Today we're going to discuss the effects of subcooling and superheating. Now, a given problem, we have a refrigerant 22, 4-cylinder, 85 by 75 compressor operating at 28 revolution per second, and a condensing temperature of 38 degrees Celsius and an operating temperature of -2 degrees Celsius, carries a refrigerating load of 112 kilowatt. The motor driving the compressor has an efficiency of 92% and draws 32.5 kilowatt. So there is a degrees Celsius for subcooling 5 degrees and 7 degrees Celsius for superheating of the suction gas entering the compressor. Now compute A, the actual volumetric efficiency, and B, the compression efficiency. So we have condensing temperature initially at 38 degrees Celsius. So if we're going to plot that one in our pH diagram, okay, of refrigerant 22, no? So drawing the dotted line, we have here your 38 degrees Celsius initially. So yun ang condition. Now, the problem said we have 5 degrees Celsius subcooling. Okay. So if we're going to deduct that one, yung 5 degrees, so 38, so that will be minus 5 degrees subcooling. So 30, ang maging temperature natin dyan, it will be 33. So zooming on the temperature natin, so we have here your 40, then this is 30 degrees, so going up. So it is somewhere here kung magiging 33 na tayo. So I'm gonna mark this one as our point for our 33, no? At this point, I'm gonna mark this one as our 33. Okay, so we have here the light color green. This is now your 33 degrees Celsius. So subcooling at 30 degrees. So lumampas na tayo sa sa saturation curve. Okay. So I'm gonna write here, this is now our 30 degrees Celsius, 33 degrees Celsius. So it is a subcooling by 5 degrees. Okay. So we have now 33 degrees Celsius. Then looking in our properties table ng R22, so 38 degrees, so we have the corresponding pressure of 1.46. So with the unit of megapascal, no? Okay, so inputting that one in our pH diagram dito. Okay, so this is 1.46 MPa. So megapascal the unit for this one. Then for our evaporator, we have the temperature -2 degrees Celsius. Okay, then we have a corresponding load of 112 kilowatt. So let's try to plot -2 degrees doon sa ating pH diagram. Okay, so we have here 0, no? Then in between there's another line which is -10, no? So this is representing our -2 degrees Celsius. Okay, then from there we're going to superheat the -2 by 7 degrees. Then yung corresponding pressure niya, so para hindi na tayo masyado mag-estimate, we refer to the table ng R22. Okay, so looking that one, okay, so we have here -2. So ang corresponding pressure niya is 0.46636, that is megapascal. Okay, so inputting that one, so para meron tayong guide and reference for this one. So, nag-superheat tayo ng 5 degrees Celsius. So, referring here, we have 0 and 10. So, that it'll be in between. So, we can assume here, dito na yun siya banda. Okay, so if we're going to plot that one, okay, so plotting that one, ito na yan. Okay, so we have here the intersection ng ano na yan, ng negative 2 to 5 degrees Celsius superheating. Okay, so I have here, I'm going to write here our 5 degrees Celsius for superheating, and this one is our negative 2 degrees Celsius. Okay, so we have here now our point 1 prime. So this is our point 1 na at this point. This is our point 1. So drawing the dotted line from the intersection, okay, so we have here the value of 410. Okay, I'm gonna write here the value of enthalpy, which is your 410. Okay, so that would be your kilojoule per kilogram. Okay, now for enthalpy, point 1, so we have H at 5 degrees Celsius and 0.466 MPa with equivalent to 410 kilojoule per kilogram. So that will be the value of enthalpy 1, referring to our pH diagram, no? Now for our enthalpy 3 at this point, so I'm gonna mark this one as point 3, no? Okay, at this side, at this point. So for our point 3, we have the corresponding enthalpy. So this is almost, this is 210. Okay, this is 10, 20, 30, 40, and 50. So we have 240, 240.5. So that will be kilojoule per kilogram of Kelvin. So writing that one, so we have enthalpy at point 3, which is 240.5 kilojoule per kilogram. Now referring to the table, so we have 32 and 34. No? So this is already in liquid state. Okay, so we're going to refer at the liquid state of the enthalpy. So well, ito na yung value niya as we go along. Mag-get natin ng value, so that will be in between 239.19 and 241.77. For process 3 and 4, we have 3 and 4, a reversible expansion at constant enthalpy from saturated liquid to evaporate the pressure to the evaporator. So we have a constant enthalpy running to this one. So this is now our point 4. Then connecting the line from 3 to 4 and 4 to 1 for the constant heat addition for our evaporator. So our enthalpy 3 is our enthalpy 4, so that will be equal to enthalpy 3. Okay, so that is 240.5 kilojoule per kilogram. Now for the process 1 to 2, so that will be reversible in adiabatic compression from saturated vapor to the condenser pressure. So we have here the constant entropy from point 1 to point 2. So referring to the pH diagram, so we have here the entropy line. So this one, entropy line. Okay, so notice here we have your entropy going up there. Okay, so intersecting from point 1 to point 2, this line, no, this line, our condenser condenser pressure, no. So we can say that our pressure, or let's say the intersection of the entropy, so this is 1.8. Okay, so if you're going to project the line going there, connecting, so it is connecting at this point. Okay, so this will be the location of our enthalpy for our point 2, the discharge pressure of the compressor. Okay. Now I draw the line from our suction pressure of our compressor from point 1 to point 2, so connecting the point 1 to point 2 at compressing the gas at constant entropy. So we have here the intersection of the pressure and the temperature. Okay, now we have now the values for the enthalpy at point 3. So this is equivalent to 440 for our enthalpy. So we have 440 kilogram for the enthalpy 2. Okay, so enthalpy at point 2, we have H at the 460. So 1460, so or 1.46 MPa. Now and at a constant entropy from point 1 to point 2, so magtatama intersection yan, we have the value which is 440 kilojoule per kilogram. So that will be the enthalpy at that point. Now connecting the line from 3 to 2. Okay, so we have connected that. Now this is the cycle of the system. So I inputted here the direction of the flow of the cycle. Okay, so looking at the overview ng cycle natin, so we have here the cycle of the refrigeration system that is being given to the problem. That is being stated on the problem. Okay, so going back to the question, the problem, so we need to compute letter A, the actual volumetric efficiency. Now for the volumetric efficiency in VA, so we have the given equation that will be the V1, so that is divided by the volume displaced. So that will be the volume entering the compressor divided by the displacement rate of the compressor. Now for B1, we have your equation, so that will be the mass flow rate. Okay, mass flow rate of entering the compressor multiplied by the specific volume of 0.1. So referring to our pH diagram, okay, so we have here the line of the density line. Okay, so you will notice at 0.1 we have malapit siya sa 20 kilogram per cubic meter, so we can assume this is 18. So I'm gonna mark here 18 our density. So we have here your density. Now our density, this is our specific volume, so that will be 1 over the density. Okay, so if we're going to substitute yung value, that will be 1 divided by 18. Okay, so this is kilogram per cubic meter. No, so the value is 0.055. So with the unit of cubic meter per kilogram, then I'm going to convert this one into liter. So 1000 liters, so we have 1 cubic meter. So the specific volume now is equal to 55.55, or let's say 56. So this will become now liter per kilogram. So we have the value now of our specific volume, but we don't have the value of our mass flow rate. Okay, so we must solve the value of the mass flow rate. Now, remembering from our heat added to the evaporator, so that will be Q at the evaporator, so that will be the mass, okay, multiplied by the change in enthalpy from 0.1 to 0.3 or 0.2 or 0.4. From here, we can rewrite our equation into mass flow rate, so that will be the heat added to the evaporator. Now divided by the change in enthalpy from 0.1 to 0.3 or 0.4. Okay. So we can substitute the Q in the evaporator, which is given to the problem. Okay. So, tingnan natin lang yung problem. So we have the refrigerating load. So that will be 112 kilowatt. No? So we can substitute that one. So we have 112 kilowatt, or let's say this will be kilojoule per second. Then we have the enthalpy of your 0.1. So looking back, so that will be 410, no? So 410 minus enthalpy 4, which is also equal to enthalpy 3, we have minus 240.5. So the unit will be kilojoule per kilogram. So we can cancel the units natin dito. So kilojoule will be cancelled out. Okay. Now we have the value of your mass flow rate. So we have your mass flow rate now is equal to, so we forgot this is 112. Okay. Then we have the mass flow rate, which is equal to 0.66. So this will be our kilogram per second. So we can compute now our B1. So that will be 0.66. It will be kilogram per second. Then multiply by the specific volume, which is 55.56. So this is 55.56. So that will be liter per kilogram. So finally, we have the value of your B1, which is equal to, so we have the value of 36.66. Okay, so we can round this one to 37. So cancel out yung common units natin dito, which is yung kilogram. So we have liters per second for the units. We have 37 liters per second. Now let's go to the volume displacement rate of the compressor. Now remembering from our previous lecture, so our volume displaced, so that will be equal to pi over 4 times your diameter d squared times your length of stroke, then the RPM. No? So checking the properties of compressor, we have 85 by 70 mm. So our 8.5 centimeter, so that this will be our diameter. So ito yung magiging diameter ng diameter ng piston, and this will be our length of stroke, 70 mm. So that will be 8.5 centimeter. And we have 7 centimeter. So we have multiplied this one by 8.5 centimeter squared, then multiply this one by 7.0 centimeter. so for our length of stroke. Then multiply by the RPM. So going back to the problem, we have 28, no? 28 revolution per second, no? And it is accompanied, it is a 4-cylinder running at the 28 revolution per second. 4-cylinder, 28 revolution per second. So substituting that one, we have 28. So that will be the revolution per second times 4 for the cylinders. And this will become our cycles. Okay. Now our volume displays is equal to, so let's add the conversion here. So we have 1000 cubic centimeter per liter, so that we may cancel out na kaagad. So we have the volume displays, which is 44.49. So the unit will be liters per second. Now let's substitute in value. We have your B1, which is 37. That will be 37 liters per second. Then divided by 44.49. So that will be your liters per second. So cancel out natin yung units dito. So we have the efficiency. So we have the value for this one is around 83.16% efficiency of the compressor. Now for letter B, the compression efficiency is equal to the isentropic work divided by the actual work. Now the isentropic work, so that is equal to the mass flow rate times enthalpy, the change in enthalpy from 0.1 to 0.2. Okay, so since that is the work of the compressor at this start, so isentropic, so here we have from 0.1 to 0.2, so the change in enthalpy from 0.1 to 0.2. Since this is the work of our compressor, so isentropic work, that would be the change in enthalpy from 0.1 to 0.2. So we have to substitute the values. So referring to our previous solution, so we have the mass flow rate, which is 0.66, so that would be kilogram per second. Then I'm gonna multiply it by the change in enthalpy at 0.2. So at 0.2 we have the enthalpy, so that will be 440. Okay, so 440 minus your enthalpy 1. Okay, we have the enthalpy 1, 410. Okay, so this one will be 410. So this is kilojoule per kilogram. So we can cancel the units here. Okay, cancel na yan. So what we have is kilojoule per second, that is already in watts. So our isentropic work is equal now to, so we have the isentropic work of 19.8. Okay, so this is the unit of kilowatt already. Now for the actual work, so that will be going back to the problem. So balikan natin yan. So we have the motor driving its compressor has an efficiency of 92%. Okay. Then it draws a power of 32.5 kilowatt. So we have the work of 32.5 kilowatt. So we have to multiply it by 92 to get the actual work. So that will be 35 by 32.5, multiply it by 0.92. Okay, then we have 29.9 kilowatt for the actual work. Now substitute it into our equation for our compression efficiency. So we have your MC, compression efficiency. So isentropic, we have 19.8 kilowatt. So divided by 29.9 kilowatt. Okay, so we have the 66. Okay, so 66.22%. So that is now the compression efficiency. Okay, so looking at the overview of our solution, so initially ginawa natin, so having a recap, so initially we have enthalpy values interpreting from the problem and pinlat natin sa pH diagram. Then we able to come up with the values of the enthalpies by using the pH diagram, since we cannot rely on morely on the table since it is more in process and subcooling and superheating. So mostly yun talaga, we refer to the pH diagram to get the values. Then to solve the problem for volumetric efficiency, so usually we have your equation, no, for a volumetric efficiency, that will be the volume entering the compressor, then displacement rate of the compressor. So step by step, hinanap natin yung values ng B1 tsaka volume displaced. So we have here, okay, then we substitute to the equation. So finally we able to come up with 83.16% for the volumetric efficiency. Now for compression efficiency, that will be the isentropic work divided by the actual work, no? So isentropic work, so that will be the change in work from point 1 to point 2. So that will be the enthalpy entering and leaving the compressor. So this part, no? So substituting yung values, and we have also the actual work of electric motor, which is given to the problem, which is 32.5 kilowatt. So we have the 22%. So that is the efficiency of electric motor. So that is how much the energy is being converted into work. So substituting that one, we have been able to determine the compression efficiency, which is 66.22%.